So today we're going to be learning about Robinson annulation, which is a tandem reaction of a Michael reaction followed by an aldol reaction followed by an aldol condensation reaction. But before we begin, we should go over some background that is important to the Robinson annulation. So a key concept of Robinson annulation is the enolate. So an enolate is formed when a base removes an alpha hydrogen. So alpha hydrogens are basically just hydrogens that are attached to the carbons directly adjacent to the carbonyl carbon. So they're right next to each other, see? So you're going to have your base, and it's going to come over, and it's going to take away this hydrogen. And in doing so, this hydrogen donates a pair of electrons to the alpha carbon, and then you have a nucleophile, which is your enolate. So sometimes we run into problems where there are two different types of alpha carbons on our carbonyl compound, and in this case, you're going to have two different enolates formed. So over here, we have our thermodynamic product, and that is formed because we use a small base because there are lots of steric hindrance right here because we have other carbons attached to the alpha carbon. So the small base, in this case, we're going to use NaOH, is going to come in and it's going to take away the alpha hydrogen, and then we're going to get this enolate. This enolate forms in higher temperatures, and it is called the thermodynamic enolate. But what if we have lots of room, and so we can use a bulky base? Well, in that case, we're going to use a bulky base, kind of like LDA. So in this case, you're going to have the nitrogen with two isopropyl groups on it. It's going to attack any one of these because they're all the same. And in that case, you're going to get your kinetic product, which has the negative charge on the alpha carbon there. So this is your kinetic product. And this specific kinetic product occurs at negative 78 degrees Celsius because that's when LDA reacts. So now that we know what an enolate is, we can go over the first step of Robinson annulation, which is the Michael reaction. So in a Michael reaction, you're going to have an alpha beta unsaturated carbonyl compound. So this right here is our alpha carbon, and this right here is our beta carbon. So in this case, the nucleophile enolate is going to come in and it's going to attack the beta carbon. And in doing that, this pi bond right here is going to flip up to be between the alpha carbon and the carbonyl carbon. And when this occurs, that's going to force this bond to flip up as well. So we end up with an ox anion, so where this, the negative charge is on the oxygen, but this is not a good state for it to be in, so it's going to tautomerize, where basically an acid is going to come in and it's going to attach to this so that these bonds can flip down and a carbonyl will be formed. So you have your carbonyl, and then basically there'll be, a hydrogen here, and then you have the rest of your compound just the way it was. So in the end, you're going to have a 1,5 dicarbonyl compound. So if you look at this right now, we have, this is our carbonyl carbon, and then we have 2, 3, 4, 5. So we did the right thing. Okay, and the next part of Robinson annulation is the aldol reaction. So in an aldol reaction, you're going to have an enolate, and it is going to attack the carbonyl carbon of either an aldehyde or a ketone or some other carbonyl compound, because the carbonyl carbon is partially positive and this is negative, so it's going to attack it. And then in this case, this bond's going to flip up, and so you're going to get another oxanion product right here. And then this is basically just going to be protonated by whatever you have in your solution. And in this case, it is water, and you're going to end up with a hydroxyl group here, and so in the end, you want the hydroxyl group to be on the beta carbon. So right here, this is our carbonyl carbon, that's our alpha carbon, and that's our beta carbon. So you want it to be a 1,3 dioxygen compound. So after this step, you just have one last step in the Robinson annulation before you put it all together. And that's aldyl condensation. So this occurs when you have heat and an acid or a base catalyst. And basically what's going to happen is you're going to form a double bond. With the acid, you have your hydroxyl group here. It's going to take this hydrogen, and then you're going to have another hydrogen here, and basically you just have water here. And that's going to have a positive charge, so it's going to want to leave. It's a very good leaving group. But now you have an electrophile right here, and so it wants the electrons on this carbon with this hydrogen. So this hydrogen is going to be taken off by actually this leaving group. It's going to take away this hydrogen, and its electrons are going to be donated to this bond, and it's going to form a pi bond here. And so in the end, you're going to have pi bond right here, and this is an alpha beta unsaturated aldehyde, because see, this is the alpha carbon and this is the beta carbon. But if you have this occurring with a base, you are just going to take away this hydrogen right away, and then you have a negative charge here, and this is an E1 carbanion because it has a negative charge, and so this is just going to flip up, and this is going to act as our leaving group, and then we have a double bond here. So now that we know all the steps of the Robinson annulation, we can go over it all together. So an annulation is when two rings fuse together. So our final product is going to have two rings. But first we have to get there. So first you're going to have your microreaction, but you need an enolate. So your enolate has to be a ring. That's very important. So you have a negative charge here. And so this negative charge is going to attack the beta carbon right here. And then, as we remember, this is going to flip up, and then this is going to flip up. And so now we have the oxanion form of our enolate, as you can see here. And this has a resonance structure of the carbanion form of our enolate. So the negative charge is going to be here because this will flip down, and then these two electrons basically just flip to right there. So once we have this, we want to tautomerize, because this is not what we want to end up with in our Michael product. We want the keto form. So we're going to take, in this case, water, and we're going to take one of its hydrogens, and then we're going to end up with this product here. So now that we're done with the Michael reaction, we need to have the aldol reaction. So we're going to take actually our product from this. And it's going to attack, our base is going to attack this and take off the hydrogen, and then we're going to form our enolate here. So once we have our enolate, we're going to have an intermolecular aldol reaction. So our negative charge is going to attack our carbonyl carbon, and then this pi bond electrons will flip up, and so then we're going to end up with an oxyanion. And so, like we remember from the aldol reaction, it's going to take this hydrogen away, and then we're going to end up with our hydroxyl group there. And the last step is, of course, condensation. In this case, we're going to do an E1CB, or our E1 carbanion. So what's going to occur is a base is going to come along, and you want to form the most stable double bond. So it would be right here in between the two rings. So we're going to have a base, and it's going to come in and take off the hydrogen, and then we're going to end up with a negative charge right here, and that's going to flip to form a pi bond, and our OH group is going to be a leaving group. It's going to leave, and then we're going to end up with our product, which is going to be a 1,5 dicarbonyl compound. So there you have it. We can count to make sure that we did it right, but because 2, 3, 4, 5. Perfect. So we have our 1,5 dicarbonyl compound. So just remember that the Robinson annulation occurs when you have a microreaction right here, followed by an aldol reaction right here, followed by an aldol condensation reaction. And it's just a tandem reaction, and they all just follow each other. It looks like a lot of steps, but if you can just remember that it's a combination of those 3 reactions, you'll be fine.